We present our paper Self-supervised relative pose with homography model fitting in the loop by myself, Bruce Muller, and in collaboration with William Smith from the University of York. In this paper, we are addressing the problem of deep relative pose estimation, where our goal is to learn the relative pose between two camera images. We choose to focus on a learned approach for speed benefits and avoid reliance on expensive sensors such as LiDAR. Competing approaches almost always jointly train both the pose and depth network, where depth is used for view synthesis, which is a very expensive and challenging approach, as you are requiring to implicitly learn thousands of parameters for generalized depth of quite varied scenes. Our question is, can we just explicitly leverage that the road scene is planar and remove altogether the need for a depth network? And so we propose to replace the depth network with knowledge of our planar geometry. Specifically, we propose to output from a CNN a ground relative pose using this pipeline to achieve approximate and then refined visual odometry in two phases. Our phase 1 method is to use a perceptual loss on the target and warped source images, where our ground relative pose facilitates the cross projection. That is, we output these 9 parameters for camera height, roll, and pitch for our camera pair relative to our localized coordinate system, which allows us to route our cameras within a local planar geometry and cross-project pixels via the ground plane with a homography. We use a frozen VGG network for feature extraction and 2 image scales to aid training convergence and train with known camera priors to help constrain our solution. In our second phase, we drop our perceptual loss and introduce the homography estimation module, which consists of 3 steps. Firstly, a leading pre-trained optical flow network is used to compute fine-scale flow between both images. Secondly, a leading pre-trained semantic segmentation network filters out the non-road parts of the scene flow. Finally, we use a robust RANSAC routine for fitting a refined homography to these planar correspondences. This refined homography is used to update the coarse homography initially output by the network. Subsequently, we decompose this homography into a camera-to-camera pose using an analytical method by Malice and Vargas. Using this decomposition presents 2 challenges. 4 solutions are generated, and then the relative translation is only accurate up to scale, which we solve by leveraging the known motion constraints from our data. The result is that we obtain camera-to-camera poses useful for both training and test time. We achieve competitive results versus leading end-to-end self-supervised deep visual odometry approaches on the Kitty road scene dataset with a relatively simple approach, which does not require to estimate many thousands of depth or optical flow parameters. Visual results also indicate that fine-tuning with model fitting helps alleviate misalignment issues seen from our initial training with perceptual loss. Trajectories also appear visually improved versus the initial phase of training and competitive against other approaches. Here we show video results of our method on Kitty VO sequence 9. For the second video, we use a much larger frame separation, which we did not train for, yet still achieve an approximate visual odometry solution. Thank you for watching, and please feel free to visit our project page on GitHub.